The purpose of a bit is to cause rock failure. Bit designs differ because rocks can fail in a number of different ways. Let's look at some of these rock failure mechanisms to see how they influence bit design and performance. Rock failure occurs as a result of stress or force applied to an area along an axis. Stress may take one of three basic forms, which can occur alone or in combination. Compressive stress, which tends to press in on or crush the rock. Tensile stress, which tends to pull the rock apart. And shear stress, which tends to slice or cleave the rock. Stress results in a deformation of the rock material. Depending on the rock type and on the magnitude of the applied stress, this deformation can either be elastic, meaning that the material returns to its original shape and size once the stress is removed, or plastic, meaning that the stress exceeds the material's elastic limit, resulting in permanent deformation. Above a certain stress limit, a material will rupture or break. If it breaks before significant plastic deformation occurs, its behavior is described as brittle. If, on the other hand, a material ruptures only after experiencing significant plastic deformation, it is considered ductile. In drilling operations, rocks generally experience brittle failure, ductile failure, or some combination of the two. Brittle failure involves a crushing or chipping of the rock material, while ductile failure is more the result of a gouging, scraping action. Under different conditions, the same material may exhibit different types of behavior. All rocks are normally brittle at atmospheric pressure. Under increasing applied pressure, however, rocks undergo a transition to the ductile state. The pressure at which this occurs varies depending on rock type and other factors. In a wellbore, this applied pressure comes from the drilling fluid column. If the pressure of the mud column is less than the pore pressure of the formation, the well is underbalanced, and brittle rock failure may occur under relatively low impact forces. However, if there is an overbalance between the mud column and the formation, the rock is more likely to experience ductile failure. In underbalanced drilling, the rock is in the brittle state and fractures very easily. Because the rock surface is in tension, it virtually explodes under the compressive loads of the bit. There is very little regrinding of already drilled cuttings. This helps attain very high rates of penetration, and is a major reason why air or foam drilling tends to give higher penetration rates than conventional overbalanced drilling using a weighted mud.
The objective in designing a bit is to take advantage of the formation's most efficient failure mechanism. If the formation is soft with low compressive strength and tends to fail in a ductile mode, we need a bit that uses a gouging or scraping cutting action. For harder formations, on the other hand, we need a bit that crushes and chips the rock. A complicating factor in bit selection is that most formations are neither entirely ductile or entirely brittle,